We're rolling, okay. So yesterday what we did is we laid out the idea of generating a membrane potential based on the potassium battery. Now, by and large, when I talk about the resting membrane potential in this class, we'll be talking about the equilibrium potential for potassium. I'll show you by the end, probably the first round of lectures here, that that's not entirely true, that there's an effective, slow, intermittent sodium current. But hold that in abeyance. Think first that we have to set the membrane potential by the distribution of potassium ions across the membrane. We did that last time. But that's not adequate for signaling. That sets up the battery. But now we have to think about doing work with that battery. And in order to do work with that battery, now we're going to invoke a new set of ions. And what we're going to do is we're going to talk about the idea of having these three ion channels work in concert. The one we talked about yesterday was the potassium leak channel. That set up the membrane potential. What we're going to do today is we're going to invoke a new channel, which is going to be a voltage gated, but it's actually going to be just a sodium channel with a gate on it. And we're going to set up the same thought experiment. We'll arrange the thought experiment where the potassium is in high concentration on the inside and low concentration on the outside. That generated because of the large negative anions and the inability of those impermeant anions to move, that generated a negative charge inside the cell. And that's where we reached equilibrium. The tendency for the potassium to leave down its concentration gradient was exactly balanced by the tendency to hold that potassium ion in place, or millions of potassium ions in place, by the electrical gradient. But now what we do is we want to invoke a new channel and a new distribution of ions. So now what we're going to do is we're going to put more sodium in the outside and less sodium in the inside. So now we have a sodium gradient. Now, initially, no sodium can move because there are no pathways. Then we're going to invoke a sodium pathway, a sodium channel. And then we're going to characterize it as being charge sensitive so we can open it. But the most important idea initially is simply going to be we have leak channels, and now we have sodium channels. And now we can think about opening and closing the sodium channels. The leak channels are always open. We can't affect them. The sodium channels we can open and close. So by opening the sodium channel now, we're going to increase the membrane permeability to sodium. And that brings us to this mantra. The mantra is the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Now, I'm going to give that to you as a mantra. If you take another physiology course, a neurobiology course, there's actually an equation that deals with this. It's called the Goldman-Katz-Hodgkin equation. It's a mouthful, but what it's telling us in that equation is that each of the ions has a voltage driving force on it. And for each of those driving forces, there is a permeability. Electrically, it's called a conductance. Put all that together, and you get the membrane potential, because you get a little bit of input from a sodium channel, a little bit from potassium, a little bit from another channel. But for our purposes, and I think the first way to think about this is to hold on to it with this mantra. It will lead you down the right road in so many different ways. To simply say the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Well, we can go back up to this story. We started out with only having potassium channels. So what's the dominant permeability for the membrane? It's potassium. So the membrane potential will seek the equilibrium potential for potassium. In biology, that's roughly minus 70 or 80 millivolts. The way we set it up mathematically yesterday, it was about minus 58 millivolts. But typically, it's minus 70 to 80. But then we can talk about another channel. We can put another channel across the membrane. We can then have these channels gated, or possibility of opening them. Then suddenly, we open the sodium channels. Now, in a thought experiment, we'll have many, many times, maybe several orders of magnitude, more sodium channels than potassium leak channels. So now what's the dominant permeability? Dominant permeability is sodium. So the membrane potential will seek the equilibrium potential for sodium. So I'll show you, but the equilibrium potential for sodium is about plus 40 millivolts. So in this way, we can change the membrane potential from the resting membrane potential of minus 70 or 80 millivolts, the equilibrium potential for potassium, up to about plus 40 millivolts, which is the equilibrium potential for sodium. But then we have to return the membrane potential back to its original resting state. We can do that with the leak channels, as long as we close the sodium channels, as long as we think of valves on the sodium channels or gates on the sodium channels, and we close them. We could use the leak channels, the potassium leak channels, to be the predominant permeability and bring the membrane potential back down, but it takes a long time. We just can't get very much charge leaving the cell through these small number of leak channels. So what we do to make the system about 1,000 times faster is we invoke a new set of channels called voltage-gated potassium channels. But again, it's the same idea. When the voltage-gated potassium channels begin to open, the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. The dominant permeability is to potassium. We're headed back down to minus 70 millivolts. And we'll talk about that oscillation. Once we've laid out this oscillation, what we have done is nothing more than change the polarity on the membrane. And that's important. It's important to be able to change the polarity on the membrane. And we're now seeing the initial stages of generating an action potential. We're generating an action potential simply by changing the polarity from minus 70 to plus 40 and back down again using these three channel types. But that doesn't give us much information about how we're going to use action potentials for long distance signaling. And we said when we talked about the structure of a neuron that the signals would start basically in the dendrite or cell body. Then we would generate action potentials, and then we would propagate those action potentials over long distances. So after we've generated the action potential with this discussion, we then have to begin thinking about how we're going to propagate it. How are we going to move it from place to place? And we're going to do this in 3 steps. The first step is going to be a case which really doesn't exist, but there are a number of ideas I want to get across here. And that is we're going to put all of the voltage-gated channels at one end of a great long cylinder. And we're going to imagine what happens to the charge that comes into the cell at these aggregated channels at one end. Now remember, in order to have membrane potential, we have to have potassium leak channels. And so what we're going to see here is that when we change the membrane potential by invoking an action potential at one point, if we have no other voltage-gated channels on the membrane and all we have is leak channels, all that positive charge which came in is now going to leak out. Now one of the ideas that you'll find confounding is that we always use potassium to leave the cell to return the membrane potential back to its original resting state. And that seems confounding because sodium's coming in, but yet we use potassium to repolarize the membrane. And I want you to know about this, and I'll discuss it here, and then we'll go into more detail in the discussion. But what I'm going to say here is that when the membrane potential goes from minus 70 to plus 40, the number of ions that have to move to change that potential is frightfully small, only a few million. And remember, we're dealing with concentrations of hundreds of millimolar. So we have lots and lots of ions. We have trillions and trillions and trillions of ions, but only a few million move to change the potential. It's because of the characteristics of the membrane, and we'll talk about that. But the idea is you don't have to move very many ions to change the membrane potential from minus 70 to plus 40. And similarly, you don't have to move very many ions to go from plus 40 back down to minus 70. Because so few ions move, it means we have not demonstrably changed the concentration gradients. We haven't changed the concentration of potassium inside very much. It goes from 110 millimolar to 109.999 millimolar. So we've hardly changed it at all. Similarly, the sodium comes in, and we change the intracellular sodium concentration from about 10 millimolar to about 10.00001 millimolar. So that's a long-winded way of saying that the only charge you have to return the membrane potential back to its equilibrium potential of potassium is for potassium to leave. Now, if that puzzles you, and it takes some practice to think through that, but if that puzzles you, go back to the mantra. Just think about what the dominant permeability is, and that will carry you to where the membrane potential is going to go as we open and close these various channels. So hold on to those ideas, but the mantra will rescue you a lot of times when you get yourself tangled. So think about that. So the first thing is membranes where voltage-gated channels are clustered at one end. The second is going to be in membranes that are unmyelinated. And in this case, what we're going to imagine is the voltage-gated channels are now evenly distributed all along the membrane. So they're like dominoes. And we're going to open one, which will open next, open the next, open the next, open the next. And that will then provide for the propagation of the action potential from place to place. But about as fast as we can go here in these unmyelinated axons is about a meter per second. But we know we have much faster conduction velocities than that. And we have conduction velocities that go up around, 100 meters per second. And the way we go from a meter per second to 100 meters per second is to do the trick we talked about yesterday, where we myelinate and wrap the axon in those insulating layers. And the idea that I'll emphasize here, and this is a physics concept, but I think it's easier to understand in biology, is the concept of capacitance. In capacitance, what's happening is we are separating charge across a non-conducting medium. In physics, you do this with wax paper and aluminum foil. But in biology, we'll do it with a phospholipid bilayer, and imagining the ions positive on the outside, negative on the inside, smashed up against that membrane, interacting with one another through electromagnetic fields like tiny magnets. They'll be held fast because it's such a narrow, such a thin insulating layer, that phospholipid bilayer. So we're going to have all this charge. Now, the next thing to think about is when we have all this charge up against the membrane, we have to discharge that capacitor before we can get significant movement of ions through the channels. So that means in these unmyelinated neurons, we have all this charge stored against the membrane that has to be discharged. So we spend a tremendous amount of energy and time that slows up the propagation by requiring the discharge of that capacitor. We walk around that point. The way we get around that, the way we increase conduction velocity, is to use myelin. And if you remember the images from yesterday, we wrap those internodal regions in myelin, and then we have these narrow gaps where we put the voltage-gated channels. Those narrow gaps are the nodes of Ranvier. And what we'll see today is the action potential will start at one node where we've clustered voltage-gated channels and move almost instantaneously through the cytoplasm to the next node. And that takes some imagination too, because when I first learned this, I imagined the sodium coming in at one node and then taking a walk to the next node. But you can't do it that way because our conduction velocities are way too fast to be accommodated by the diffusion of the ions. So what we have to invoke and we have to think about is this electrical concept of each of the ions has an electromagnetic field on it. When all of these few million ions come in at the node, they carry with them this electromagnetic field. The electromagnetic field now can be propagated almost instantaneously through the saltwater solution of the cytoplasm, the exoplasm, to the next node. So we don't have to have these ions move from place to place. We simply use their electromagnetic fields moving through the aqueous environment of the cytoplasm to the next node to open those channels. That way we can almost instantaneously move from node to open those channels and increase conduction velocities to about 100 or 110 meters per second. And we'll walk our way through that in some detail. And then where I want to finish is to talk about something known as frequency coding. And one of the concepts we'll try to drive home today is that these action potentials, once they start, they're all or none. They go to plus 40 millivolts and they come back down to rest again. And that's an all or none signal. We'll see they have something known as a threshold. Once you get enough positive charge inside the membrane, off it goes. There's no stopping it. You go up to 40 millivolts. Well, how do you take a signal that's always the same amplitude and always the same duration, and how do you encode information in that in a biological system? The simple answer to that is something called frequency coding. We don't care so much about the shape or size of the individual action potential. They're all the same. But what the neuron cares about is how many are there and how fast they occur. And those signals are going to now be transmitted to the terminal, the axon terminal, where those signals are going to open channels, voltage-gated calcium channels, that will allow for neurotransmitter release so we can talk to the next cell. But that will be tomorrow's story when we talk about synapses. But let's start here. Again, with the concept of the resting membrane potential. Now, it's a bit of a lie, and I'll tell you why and how it's a bit of a lie later on in a slide. But for now, we're going to say the resting membrane potential is the same as the equilibrium potential for potassium. So let's rethink how we got to the equilibrium potential for potassium. We have these two membranes. We can imagine this is a cylinder. We said that the concentration of potassium on the outside in our thought experiment, and we'll do it again as a thought experiment, is 10 millimolar. We said the potassium concentration on the inside, should put a little O out here, is in the neighborhood of 100, and we'll say 100 millimolar in our thought experiment. Then across the membrane, we put specific channels, not very many of them. We put specific channels called potassium leak channels. We said these potassium leak channels are always open. They never close. I guess they're like 7-Eleven. So these channels are always open, and then the next set of ions out here is going to be sodium. And we're going to put these on the outside. And we're going to say that this is about 100 millimolar. Again, these are not biological. Just as I said yesterday that biological numbers for potassium are 4 to 5 millimolar, biological numbers for sodium are 130 or 140 millimolar. But for our purposes, I think it's easier to work with these round numbers. And then on the inside, we're going to say the sodium concentration on the inside is 10 millimolar. The way we finished yesterday was we said that on the inside of the membrane, we had these large negative anions. They were impermeant. They couldn't go anyplace. They were stuck. And we invoked them for setting up the charge difference across the membrane. We said that what would happen is that this potassium would begin to run down its concentration gradient, going from high concentration to low concentration. But then that movement will be held in check. It will be held in check by the charge on the negative charge on the anion, holding those potassium ions in place. And that then created an equilibrium, which we said was the equilibrium potential, EK, for potassium. And we gave this an equation. We said EK equals RT over ZF times the natural log of the potassium concentration on the outside divided by the potassium concentration on the inside. And we made these numbers work because we said we could change this constant and the natural log to a constant, and we said, okay, at room temperature, we can say that EK equals minus 58 millivolts. And that arose because the concentration of potassium on the outside was 10, and on the inside was 100, and the log of 10 over 100 is minus 1. So we come up to EK equals minus 58 millivolts. That's where we were yesterday. We set up the resting membrane potential. And you had a question in the back.
Yeah, what are the anions made of?
What are the anions made of? Some of them are thought to be proteins. Some of them are thought to be large organic acids. And it doesn't much matter. The major idea is that they have all this excess negative charge on them, and they can't move. They're stuck. And because they're stuck, they can now form a kind of barrier to prevent the loss of that potassium. We reach an equilibrium.
And then we might touch on this question a little, but for the Na, the sodium, how does the sodium enter? Is it through the voltage meter?
Okay, so that's where I'm headed now. The question is, how does the sodium get into the cell? And let me walk you through that. We have this gradient. Notice we have 100 millimolar sodium and 10 millimolar sodium here. So we have a tenfold gradient to bring the sodium in. What's more is it's negatively charged inside the cell, and the sodium is positively charged. So there are two gradients driving the sodium into the cell, the electrical gradient as well as the concentration gradient. And the question is a good one. Why is it we don't have any sodium coming into the cell? Well, the answer to that question is we have no channels. We have no pathways. These blue leak channels only allow potassium to move. So the way I've drawn it so far, we have not put any pathways for sodium across the membrane. So now let's imagine putting some pathways for sodium across the membrane. I'll put these in red. Label these as sodium selective channels. Well, if we were to do that and only make them sodium selective, you could see where we wouldn't make much progress. That basically the sodium would come rushing down its concentration electrical gradients, and it wouldn't take very long before the ocean, which is at 100 millimolar, reaches the same concentration inside the cell. So what we have to impose a limitation on these sodium channels. The limitation we're going to put on the sodium channels is they have gates. Because they have gates, they're now no longer permeable to sodium. And under these circumstances, the way I've drawn this, the only permeability is to potassium. And the mantra says the membrane potential will seek the equilibrium potential for the ion whose permeability is dominant. So the membrane is predominantly permeability to potassium. So the membrane potential is going to be down around the equilibrium potential for potassium, which in our thought experiment is minus 58 millivolts. But in reality, it's probably about minus 70 millivolts. So we're stable here. We've set up a stable situation. But now let's destabilize it. And the way we're going to destabilize it is we're going to imagine opening these gates. So under this sort of stable arrangement, the sodium is trying to come in. You can imagine it knocking on the door of the gate, but it can't get through the gate. But what happens if we open the gate? If we suddenly open all of these gates, we'll see in a moment how that gets done. But let's just now, in a thought experiment, imagine that we open all of these gates. And let's say that there are 100 times more sodium channels than potassium channels. Let's use the mantra. If we now suddenly open all of these sodium channels, what if we increase the membrane permeability to? Well, to sodium. And if there are a lot more of them, we now can say we have 100 times more permeability to sodium than we have to potassium. Back to the mantra. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Well, we can do the same thing for sodium. For each of the ions, in fact, we can set an equilibrium potential. So we can do the same story here, and I'll use the magical numbers. We can say that E sub Na is equal to RT over ZF times the log, natural log, of the sodium concentration on the outside divided by the sodium concentration on the inside. Well, I won't belabor too much. We've said that this is going to convert to 2.72. This is a constant at room temperature. And so again, we have the same thing. We have ENA is equal to 58 times the log of the sodium concentration on the outside, which is 100, divided by the sodium concentration on the inside, which is 10. Well, that, of course, is equal to 10. The log of 10 is equal to 1. So now, the equilibrium potential for sodium in our thought experiment here is plus 58 millivolts. So in our thought experiment, we started out with the equilibrium potential of potassium because the predominant permeability across the membrane was to potassium through the leak channels. And then we put in these sodium channels, and it didn't change much because they had gates on them and the gates were closed. But then we invoked the idea that suddenly we opened all of those gates. And the permeability now is predominantly to sodium. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. We're headed toward the equilibrium potential for sodium. So let's graph that. So let's take a look at it this way, where this is voltage, and this is time. And we start out at a membrane potential. I'll use the one we have here. We're going to start at minus 58 millivolts. And then at this point where we have the arrow, suddenly, in a magical way I'll describe a little later that happens in biology, suddenly we open all of these sodium gates. The membrane potential now will seek the equilibrium potential for the ion whose permeability is dominant. So almost instantaneously, the membrane potential goes from minus 58 to plus 58 millivolts. As long as these as long as these sodium channels are open, what's the predominant permeability? We only have maybe 10% or 1% as many of the potassium leak channels as we have sodium channels. So what's the predominant permeability? It's sodium. And as long as these channels are open, the membrane potential is going to stay at the equilibrium potential for sodium, which in our thought experiment here in our model system is plus 58 millivolts. But yet we know that we have to return this thing back to baseline. If we're going to continuously use the energy we stored in the battery, we have to return this membrane potential back down to its original rest. So how do you think we'll do that? Well, the easiest answer is to, once we have opened these channels and increased the membrane permeability to sodium, we now need a trick to close the channel again. I'll tell you what that trick is a little later. But right now, we're going to go from the open state back to a closed state. Well, if all the sodium channels are closed, what does that say about the permeability to sodium? It's down. There's hardly any at all. So what's the predominant permeability? It's the only channel we have. It's potassium. So that's going to drive the membrane potential toward the equilibrium potential for potassium, so the membrane potential is going to come back down again. Now, this is through potassium leak channels. And the system will work that way. As long as you have a permeability to potassium, you will return the membrane potential back down to its resting state near the equilibrium potential for potassium. But what you have to recognize here is we just don't have very many of these leak channels. So if we want to speed this thing up, in fact, I should say that the rate at which this would happen is probably to get back down to the resting state would probably take seconds to minutes. But we know that from measurements of neurons that neurons can often fire 100 times a second. So that means there has to be something to make this repolarization event much, much more rapid. And so what we'll do is in the biological system, we're now going to invoke a third set of channels. So what we've done so far is simply talk in terms of a sodium channel and a potassium leak channel. But now across the membrane, we can put another channel type. And this channel type that I'm showing in green is said to be a voltage-gated potassium channel. Well, there's meaning in this term, voltage-gated. When I say voltage-gated, I could equally say charge-sensitive. And these voltage-gated potassium channels are sensitive to positive charge. So one of the things you have to recognize here is that initially, with the large negative ions on the inside and the separation of charge by the potassium battery, that there's an excess of negative charge on the inside of the membrane. So at rest, there's an excess of negative charge on the membrane. And then on the outside, lined up with those negative charges, will be positive charges. But what happens here is that when we open the sodium gates, the sodium channel gates, sodium comes in, and it brings with it positive charge. Remember that sodium is moving down both its concentration and electrical gradients, and so now what we have done is we have replaced these negative charges along the membrane with the positive charges of sodium. And here's the thing that takes a little bit of practice to think about. And this is the idea that we can change let me spell this out. The membrane potential can change by moving a small number of ions. Any of you who like numbers, I'll give you the numbers here. There's an exercise in one of the in the ebook to walk you through this, but it's an important idea that says Q is equal to CV, where Q is the number of charges and C is the membrane capacitance. Which, by the way, is always 10 to the minus 6th farads per centimeter squared. And then times the voltage. And if you work your way through this and use the capacitance of the membrane and how many square micrometers you have and so on and so forth, what you'll find is typically that when we have an excursion from, say, minus 70 millivolts to plus 40 millivolts. This is 110 millivolts difference. By looking at Q is equal to CV, if you actually go through the numbers, you can take my word for it, but you can go through the numbers. The number of ions that will typically move in a typical neuron to change this potential are such that it changes the sodium concentration from, say, the inside sodium concentration, changes the inside sodium concentration, because of delta, sodium concentration inside changes from 10 millimolar to 10.0001 millimolar. What I'm saying here is it doesn't take very much, it doesn't take very many charges, a few million, to change the membrane potential by a whole lot. The other idea that this describes is that the concentration of sodium after an action potential inside the cell has hardly changed at all. Hold on to that idea. That's an important idea. Similarly, we can say that the potassium concentration on the inside, the change in the potassium concentration during an action potential goes from about, 110 millimolar to something like 109.9999 millimolar. those are just numbers to try to convey to you that we don't have very much of a change in concentration of ions. We can change the electrical signal, we can change the distribution of ions without moving very darn many of them, leaving the concentrations of the ions relatively unchanged. That takes a while to get your head around, but take my word for it, or work through the equation if you don't want to take my word for it. But the concentration on the inside of the cell hardly changes at all with an action potential. What it means then is that we can have many, many, many action potentials before we affect the concentration inside the cell hardly at all. And I tell this story predominantly because what I want you to hold on to is that all of this movement of ions across the membrane, sodium coming in, potassium going out, all of that occurs without changing the concentration. That presents a kind of problem, because when we go in our action potential up here, we haven't moved very many ions. And there's a tendency, students desperately want to tell me that we're going to use sodium to repolarize the membrane. But we can't use sodium to repolarize the membrane because we still have the wrong gradients. We still effectively are 10 millimolar inside and 130 millimolar outside. So we simply can't use sodium. It's in the wrong direction. So the only charge carrier we have is potassium. And we'll use potassium then as a positive charge to carry the electrical charge out of the cell and repolarize the membrane. But you can think about that entirely by the mantra. Membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. But you have to hold on to the idea that the concentrations aren't changing. So the only way we repolarize the membrane is through the use of potassium ions leaving. Yes?
So for the the sodium channels, are they a one-way pathway, or do they go both in and out?
So it's a great question. The question here of these sodium channels, the red sodium channels, the question is, do they allow ions to flow in both directions? And the short answer to your question is yes, they don't care. They're just open pathways. And what allows the sodium ions to move in one direction or the other is simply the concentration gradient. And they've done this in the early days of trying to sort out how action potentials worked. What they would do is they would take a squid giant axon. The squid are these unusual cephalopods, and they have these great big axons that are as much as 1 millimeter in diameter. And they literally, in the early days, they could take a tiny squeegee and they could squeeze the cytoplasm out of one of these axons. And then they could infuse the inside of that axon with whatever ion solution they liked. And when they did that, they found that there was nothing magical about these sodium channels in terms of which way they would permit the ions to flow. They will permit the ions flow in either direction. That's true for the potassium channels as well. It's just all based on the concentration. And your point's well taken, because what we're saying here is that the only way we're going to get sodium to move through these channels is to use the energy of the gradient, where we have so much more sodium in the outside than the inside. And similarly, the way we allow positive charge to leave the cell is by opening the voltage-gated potassium channels, lightly allowing the potassium to leave and bring the membrane potential back down to its equilibrium potential for potassium. Does that answer your question?
Yeah, but I have another question after that. So for the sodium channels specifically, if they're gated, why would they be gated if they still want things to both enter and exit at the same time?
I'm sorry, could you ask that again?
What opens the gates, I guess?
Okay, what opens the gate? Let's hold that one, hold that thought, because that's where we're going to go next. And we'll see that what opens the gate for the voltage-gated sodium channels is just as I said here for the potassium channels. They're charge sensitive. We'll say they're voltage gated, but it's the same thing as saying they're charge sensitive. They're recognizing a change in charge. And in the case in the case of both of them, they're recognizing an increase in positive charge on the inside of the membrane, and that swings the gate open. Yeah?
What did you say happens to the negative anions after the depolarization happens?
The impermeant ones?
Yeah.
So the question is, what happens to these large impermeant anions after the action potential? They don't go anywhere, but their charge will be swamped, be overcome by the influx of the sodium.
So then, but you still need the voltage-gated channels for the sodium to leave, even though the change has...
Okay, so we don't need a voltage-gated channel for the sodium to leave.
Potassium.
Right, potassium.
Right.
So-
I'm saying if you said the charge changes on the negative anions, then why wouldn't they be able to just follow against there?
So what will happen when these when the green potassium channels open, now you have a gradient for the potassium to go out, right? So because we haven't changed the concentration of potassium, it's still 100 or 110 millimolar inside and 10 millimolar, 4 to 5 millimolar outside. There's a whomping gradient to drive it out. Okay with that? But also we will have these negative charges at the inside. They'll also help drive at that point. They'll help drive the potassium out. But predominantly, the potassium is moving down its concentration gradient, and it comes back to equilibrium. And this is your question. It comes back to equilibrium when we reach the negative charge of the negative anions balanced by the tendency of the potassium to leave. So we go back to that equilibrium. But
My question is that they can't leave through the leak channels. They can't exit through the leak channels.
okay, so they can't. So the question is, can they leave through leak channels? Yes, they can leave through leak channels. The only reason we have to invoke the voltage-gated potassium channel is speed. Because this action potential, and maybe I should draw it more accurately, if this were a typical action potential, we'd see it goes up to plus 40 and comes back down. It looks a little bit like that almost immediately. And the duration of this thing is about 1 to 2 milliseconds. Whereas if we were entirely dependent upon the leak channels, it would take minutes, seconds to minutes. So we simply speed up the event of the potassium leaving by opening those voltage-gated potassium channels. The leak channels will be carrying some, but they just, again, this is where it's easier to think in electrical terms, they just won't be carrying very much current. If you measure the current, which is the number of ions that are moving per second, during the repolarization phase, when we're bringing the membrane potential back down again, the predominant current here is going to be potassium through the voltage-gated channels. You get a little bit of current through the leak, but the predominant current is going to be through the voltage-gated channels. Yes?
Is there more to the story of what happened to the sodium? So I'm assuming, like you said, the sodium comes in, it's not going to go back out of the cell. I'm assuming we don't just have sodium pumping in for our whole life.
Your point's really well taken. And your question is, well, what happens to the sodium? And you're right. If you run this for very long, this gradient is going to wear down. What I'm trying to impress upon you right now is that you can have many, many action potentials before that gradient breaks down. But you're absolutely right. Over time, you're going to have to invoke something we're going to run into over and over again called the sodium-potassium pump. And the sodium-potassium pump uses ATP, but it's bailing out the sodium.
Yeah.
And why I am always reluctant to talk about the sodium-potassium pump is because students really, really want to think about sodium concentration on the outside becoming equal to the sodium concentration on the inside with each action potential. And so then you're told that, well, you need a sodium pump in order to do that. Well, that ain't true. You only need the sodium pump for long term. The way I think about it is in an everyday life is your cell phone. So you know full well that you don't have to recharge your battery every time you send a text message. So you've stored all this current, all these electrons in your battery, and you use them to send your text message. And you send 10 or 100 or 1,000 text messages. And you'll watch the battery come down because you've used those electrons. And so eventually, you've got to go charge the battery in your cell phone. But each individual sending of your text message does not require a recharge of the battery. It's analogous to this. Each action potential can be thought of as a kind of text message. Send enough text messages, yeah, sure, you're going to have to recharge it. But we can send a lot of action potentials before we have to recharge this battery. And it's the recharging that's done by the sodium-potassium pump. Sodium-potassium pump is pumping sodium out and is pumping potassium in.
It gets back to that idea of it's such a minimal change in concentration. It's just a second. You have the big change, you got to pump the potassium up to get back to reset. But the sodium coming in is so small, like you said, okay.
Right, exactly. That's exactly it. Now, well, I hate to tell this part of the story, but it's true. If you look at really, really tiny axons, where they have a fairly large volume to the surface area ratio, you actually will change you'll actually change the concentration with a few action potentials. But I don't want to tell you that story, because I just find it kind of confusing. But if you really imagine typical neurons can carry many, many action potentials before they have to recharge the battery. And the recharging true is the sodium-potassium pump. But so many people, I can't tell you how many students carry an idea into this course that it's the sodium pump which generates the action potential. It's not the sodium pump that generates the action potential, it's the separation of charge. And we can separate that charge. Well, over time, we need the pump to separate the charge. But we can poison the pump and still have that charge separation, at least for a while. So now that I've gone farther and farther into the weeds, are there some questions on that? Yeah.
Just a quick clarification, so then would it be fair to say that the sodium-potassium pump functions basically as like a backup to maintain the gradient or the charge?
It's a kind of backup, but I don't know if this is an apt analogy or not. I don't know how many of you have ever been on a ship, but on a ship there's constant water leaking in. And so there are bilge pumps. So you constantly have bilge pumps that are pumping the water out. Now, if you get to the point where the water's coming in faster than the bilge pumps can carry it out, you've got a big problem. But the bilge pumps are constantly working. And you can imagine that a cannonball comes through your hull, and now you have a lot of water coming in at that site. The bilge pumps have to work harder. But by and large, the leaks are slow. In a normal old wooden ship, the leaks are slow. But the water's coming in, but as long as the bilge pumps are faster than the leak, then you can maintain a steady state. It's just like here. As long as the pumps can maintain those gradients over the long haul, then you can use those gradients to fire action potentials. Does that clear it up?
I think so.
Okay. Yeah.
So I'm not clear, is the sodium potassium pump doing the opposite of what the action potential is doing? Because it sounded like you were saying with this, sodium is coming in, and that's what increases that voltage, and then potassium goes out, and that's what returns it to.
Yes, sodium comes in to change the polarity from minus 70 or 80 to plus 40. Potassium goes out to return the polarity to minus 70 inside of the cell. Okay, but that's the electrical signal, and that happens fast. And we can have many, many of those electrical signals before we demonstrably affect the concentration. But given time, if we integrate this over a long period of time, then we have to do something with the bilge pumps to make sure the ship doesn't sink. So the bilge pumps are constantly working to move that sodium out that's come in. But that's not to say that each action potential requires the removal of the sodium that's come in so that you can have another action potential. That's just done by the gradients. It takes a little practice to think about that. But one is a very rapid, short time frame, millisecond. The pumps are working continuously over long periods of time. Now you're right, in cells where you have, say, 100 action potentials per second, and there are some that go that fast, then those bilge pumps are working mighty fast to try to get that sodium out. But that's a longer time. It's integrated over a longer period of time.
And are those pumps channels?
Are the pumps channels? No, the pumps, if we imagine the pumps, what they are is they're transmembrane proteins. And they'll grab 3 sodium ions in the inside and 2 potassium on the outside. And the sodium go out, and the potassium come in. And that requires the cleavage of molecule ATP to ADP. So we use the chemical energy we've talked about in adenosine triphosphate. We use that chemical energy to power these pumps. And the powering the pumps by allowing the sodium, by basically changing their configuration. So they'll stick sodium on the inside, potassium on the outside, and turn them around. But remember, we're working against a gradient here, because there's always so much more sodium on the outside than the inside, so much potassium on the inside than the outside, that we need to expend energy to work against that gradient. Anything else before we take a break? Let's take a break, and then I'll come back and answer the question about how we gate these channels. talk about these voltage-gated sodium channels. And the way we described them is we said that there were these channels across the membrane that had these gates. But what we didn't describe in that discussion, we talked about it for the potassium channels, what we didn't talk about for the sodium channels was that the channels, I should say channel opening, depends on their charge sensitivity. Now, another way of thinking about that is that if we have this membrane, and across the membrane we have a channel, and it has a gate on it, that we need, the sodium is trying to come down through that channel, down its concentration gradient, but it can't get in because the gate's closed. So the question we want to ask now is, how do we open the gate? The simple answer is charge. By adding charge on the cytoplasmic side of the membrane, the addition of this charge tells this gate to swing open so that now we can use the gradient to allow sodium to come in. And if you understand that these voltage-gated channels open because they recognize an increase in charge along their cytoplasmic side, that's all I'll ask. But we understand how this works now. We understand in great detail. And I'll tell you that each sodium channel contains 4 regions called S4 regions. These are transmembrane regions. From what we've talked about before, you'll remember that when we talk about the way these proteins go across a membrane, so let's put in a proper phospholipid bilayer. Then when they go across the phospholipid bilayer, they go across the membrane as an alpha helix. Well, the voltage-gated channels have like 24 different transmembrane regions. And one of those 24 is called S4. This is a transmembrane helix. Now, on that transmembrane region of the helix, there'll be charges. And there'll be R groups. It turns out on the S4 region, there are a certain series of negative charges that line up with another transmembrane region. No, I don't remember which one it is. It may be a couple of them, which also have on them predominantly arginines, which are positively charged. So at rest, this is stable. These negative charges on the S4 region are interacting with positive charges on the other alpha helix. So everybody's matched up, charge to charge. The negatives and positives are attracting one another, and that's stable. But now suddenly, in one way or another, we'll see later this is done mostly by ligand-gated channels in the input region of a neuron, but in some way we add positive charge. We've now disrupted the equilibrium. This positive charge repels the positive charge on, oh, I did it backwards. This is the S4. And this is the other. So now this positive charge repels the positive charge on the S4, and they switch positions. They move just a little bit, only a few angstroms. But when 3 of the 4 of these S4 regions move in that direction, because they pop out of the membrane just a little bit, and they're forced to pop out of the membrane because the positive charge has caused these nice equilibrium, positive, negative, to be put in disequilibrium, then those will move with respect to one another. Okay? So the positive charge forces this guy up, pops it up. Imagine it a little bit like those thermometers you have in your turkey at Thanksgiving, and when the turkey's done, the little red button pops up. Imagine that's what's happening here. This is popping up. But when this S4 pops up, it's actually mechanically connected to the gate. And the moving of the 3 S4s, any 3 of the 4, by moving them will actually tug on the gate and pull the gate open. I'm astonished that at these molecular dimensions, we actually have a mechanical state of opening the channels. But that's how they work. So that's way more detail than I'll ever ask on an exam, but recognize that it provides, I think, an exquisite explanation of how we can use charge on the inside of the membrane to change the configuration of the voltage-gated sodium channel to pull on the gate to now allow for open access for the sodium to come in. That's how those channels work. But now let's look at a little bit more detail and describe an action potential. And I'm going to put a couple of more ideas in here. So we described that action potential in pretty vague terms. Now what I want to do is talk about the timing of the action potential. And this will include the concept of threshold. We typically talk about an action potential as being an all or none stereotype signal. Always looks the same. Has pretty much the same duration, pretty much the same amplitude. And it's all or none because there are characteristics of the membrane and characteristics of the channel, which once we reach a certain amount of positive charge, it goes off. It goes off explosively, all at once. So we'll spend a little bit of time talking about that and see if we can drill down and think about this sort of conceptually. And I'll do this by drawing our curve where this is time and this is voltage. And we start out at minus 70 millivolts. This is close to EK. We're going to call it EK for all intents and purposes. And all of that's stable. It's equilibrium. But then let's imagine that we start flickering the sodium channels, one at a time. Well, each time a sodium channel opens, it lets in a little positive charge. Each time it opens, it lets in a little positive charge. It lets in a little positive charge. Now, if these flickerings are not consistent, then there's adequate potassium leak channels to return the membrane potential back down to rest. So as long as the dominant permeability is to potassium rather than sodium, and we don't have enough channels opening to get the permeability to be dominant to sodium, we're not going to reach a magical level here called threshold. Now, threshold varies from cell to cell, so I give a round number, more or less. It's about, minus 55 millivolts. So we can imagine here that we add a little positive charge, one way or another. Positive charge, positive charge, positive charge, positive charge. But as long as the predominant permeability is potassium, we don't reach this magical level, the membrane potential comes back down again. But if we add enough positive charge here, until we reach this magical level, until we exceed the magical level called threshold, above threshold, we fire an action potential. Well, threshold has a definition, and I think it may help you understand this. Threshold is defined as the point, the voltage, sodium influx through voltage-gated sodium channels exceeds potassium efflux through voltage-gated potassium channels. Well, that verbiage is exactly what we described here. When we reach this magical point, threshold, we're kind of on a teeter-totter. We're on a knife edge. And at that knife edge, if sodium influx becomes greater than the ability of the potassium leak channels to carry the charge out, we're going to start accumulating charge. As we start accumulating charge, back up to the upper panel. As we start accumulating charge around the cytoplasmic side of these channels, as we accumulate charge here, these gates open and bring more sodium in. So when we reach threshold where sodium influx exceeds potassium efflux, this point at threshold, this leads to, and I'll put this in quotes, explosive opening of nearby voltage-gated sodium channels. Another way of thinking about this is when we reach threshold, we now have enough positive charge, usually in the form of sodium, aggregated around the cytoplasmic side of the channel, that now these sodium channels begin to flicker open. And as they carry more sodium in, they deliver more positive charge to the neighboring voltage-gated sodium channels. So now everybody starts to open and open and open. So you have this explosive event of all the sodium channels opening at one time. And during this period of time, you have high permeability to sodium, because sodium channels are opening. Suddenly all these sodium channels open. Now what's happened at that point, now all the sodium channels in that local region around the membrane, not all along the membrane for miles, but around the, are open at one time. So that tells us that the predominant permeability is to sodium. That's why we drive the membrane potential up here toward EK. And this sweeping increase in the sweeping increase in the voltage, where we go from minus 70 to plus 40, this is called a depolarization. We had started out with the membrane polarized at minus 70 or 80 millivolts. And we depolarize that potential by allowing sodium to come in and offset all those negative charges. Now, from what I've just described, you would imagine here that we're going to hang out at the equilibrium potential for sodium forever, as long as those gates are open, and that's true. But what happens near the peak of the action potential is someplace up here, we begin to see something called the inactivation of the sodium channels. If you talk to a biophysicist, they'll tell you that there's a real difference between inactivation and closing. I think for our purposes, we don't care. They have different mechanisms. But in fact, what's happening here is that the inactivation of the channels is saying that the sodium channels become closed. commonly, the way we refer to this, more or less anecdotally, although there's some truth to it, is that we imagine across the membrane we have a channel. We'll make this a sodium channel. It has a gate on it, but it also, the way it's commonly depicted is down here, it has an extension into the cytoplasm. So down here we're in the cytoplasm. And there's an extension called a ball and chain. We now know that's not a completely accurate description, but it is a series of amino acids, and it can swing. And because these amino acids can swing, you can imagine as a ball and chain. And what will happen is that this ball and chain is just kind of swinging down here, but doesn't do anything as long as the gate's closed. But when the gate opens and sodium starts to come in, then this ball and chain, which is swinging around here, will actually swing up into the mouth of the channel and block the channel. Turns out it's a fairly short segment of amino acids on the cytoplasmic side of the voltage-gated sodium channel. But when this ball and chain, or a series of amino acids, moves into the channel and blocks it, this is said to be inactivation. You've effectively plugged the channel, and by effectively plugging the channel, you stopped sodium influx through that channel. Just basically plugged it up. So at this time, we're inactivating the channel. At that point, as we inactivate the channel, remember we have all this positive charge on the inside of the membrane because the sodium has carried positive charge inside. So we have all this positive charge in the form of sodium. And the other character here is these voltage-gated channels called voltage-gated potassium channels. So the ball and chain has moved into the mouth of the sodium channels, and we no longer have sodium influx. So we've stopped the sodium influx. We call that inactivation, but if you think of it as closing, that's fine. And at that point, we now invoke the positive charge to open these voltage-gated potassium channels. These particular potassium channels, and if you take a neurobiology course, you'll find that there are like a dozen of these different potassium channels. This particular one has a name, and I really like this name. It's called the delayed rectifier. And there's meaning in that term. It's delayed in time. So where the sodium channels open really, really fast, they're quick. They see that change in positive charge and they open almost immediately. I think of these channels as sort of being lumbering. They see the change in positive charge and they ignore it for a time being, and then they open. So they're delayed in time. But the rectifier also has meaning because it's rectifying the membrane potential. So if we go back to this image up here, at just about the same time the sodium channels are inactivating, the voltage-gated potassium channels are opening. Again, the mantra. The dominant permeability is now going to be to potassium. So we're going to drive the membrane potential back toward the equilibrium potential for potassium. So go from plus 40 or so back down to minus 70. We come back down to EK. So what we're saying here is that by adding positive charge to a resting membrane with voltage-gated sodium channels in it, that positive charge can cause the gates on the sodium channels to swing open. And when those gates swing open, we can now use the gradient of sodium to sodium come rushing in. That changes the membrane potential. It doesn't take many of them, but it changes the membrane potential from minus 70 to plus 40. And then, after we've reached the peak, or about the time we reach the peak, the sodium channels begin to close because they inactivate the ball and chain. And then the slow responding voltage gated potassium channels open and repolarize the membrane. That's the crux of what we have in an action potential. Let's take a minute and look at some figures of these sort of stylized images of these channels. This first image is just one where it describes, this is in the ebook, and it describes how the distribution of charge across the membrane is generated with these large negative anions, so that the potassium channels flow down the concentration gradient until they reach an equilibrium with the large negative anions. And once equilibrium is reached, the probability of potassium ion coming in is the same as one leaving. We've reached equilibrium, and that equilibrium is a balance between the chemical gradient, the difference in charge, the difference in concentration is balanced by the difference in charge of the negative anions and the positively charged potassium ions. But then we begin to drill down and think about the channels. This is an example of a voltage-gated sodium channel. And it has all the characters we just talked about. So that here's this channel in the closed state. Here's the gates closed. So this is highly diagrammatic. But the gate's closed. Now we add positive charge in one way or another. We could do it experimentally by pumping charge into the cell. We could do it in a neuron by opening neurotransmitter operated channels. It doesn't matter. Some way we have increased the positive charge at the site. By increasing the amount of positive charge, if we get enough positive charge accumulated around enough of these sodium channels, then these guys start to open in such a way that they open explosively, and all the sodium comes rushing in to polarize the membrane potential to about plus 40 millivolts. But then this seems to be stochastic. It seems to be random. These guys just wander around down here, and then randomly the ball and chain moves into the channel, plugs the channel. That stops sodium influx. This is inactivation. So this is resting state, open, inactivation. Now that's for sodium, so that's for carrying positive charge into the cell, but now we have to carry positive charge back out of the cell. And the only character we can use to allow the charge to leave is to use the potassium gradients. We explained that before break. And this is the channel we're going to use for that. Again, it's voltage gated. So we have a gate on it. It's charge sensitive. We get enough positive charge around it, the gate swings open. When the gate swings open, potassium now flows down its concentration gradient, carrying positive charge out of the cell, carrying the membrane potential back to the equilibrium potential for potassium. And then the gate closes again. You notice there's no inactivation gate on this. There's no ball and chain. That's a characteristic of these delayed rectifiers. They don't inactivate. So you have sodium channels which inactivate, and these voltage-gated potassium channels that don't inactivate. It's one of their major differences. If you take another course and start studying these channels, you find some potassium channels do inactivate. We're not going to talk about them. So any questions on what we've done there? Yes?
With the ball and chain on the sodium channels, is there like a time at which the ball and chain is coming back down into the cytoplasm and the gate is closing that allows for any additional sodium influx?
Okay, so the question here is there a time when you get a kind of mismatch between the gate which is closed, or I'm sorry, the gate which is open, and the ball and chain moving in and resetting? The answer to that is basically yes. And it's one of the reasons that the biophysicists want to talk about inactivation rather than talking about channel closing. Because in order to get that channel to be into an openable state again, we have to repolarize the membrane. So you can imagine, if we go back, you can imagine that this gate will open. You could imagine a system where you had to close it again to inactivate it, but it doesn't work that way. You inactivate it, the gate in many cases will remain open, but nothing flows. But before we can reopen it again, before we can return it to this state, two things have to happen. We have to pull the ball and chain out, and we have to close the gate. Those S4s have to come back down across the membrane. So that's why biophysicists want to separate it. They want to say there's this action which occurs to activate the channel, and then there's another action that occurs that requires you to put the gate back into its closed spot. You don't leave it open unless things go wrong. There are some mutations that allow that, but for the most part, these are two separate events. And before you can reopen the channel again, that gate has to go back into its old place. And my understanding, it goes back into its old place because the S4s, when you repolarize the membrane, those S4s come flopping back down into their old status, being lined up with the negative charges on neighboring alpha helices. And then they're no longer tugging on the gate, so the gate moves back into its closed position. So the S4s have opened it, but then as they move back down across the membrane, that will allow the gate to close. But that's a separate event from the inactivation. And that's why biophysicists separate them, because they're separate events. They're separate in time and separate in, I think, in the biophysics. Does that answer it? Sorta? Ish.
I guess more specifically, I'm wondering that, like, is that inactivation and reset, is that coordinated enough? Because it seems like just by looking at the diagram that there would be like a moment in time where the channel is not active, but it's still open, where that exchange is occurring between the gate and the ball and chain. So
I don't think I have a good answer for you. But the story that I have is that you can't, once the gate is open and the channel is inactivated, it can't go back to an openable state until we move the gate closed again. But what you're asking, and I think the biophysicists would tell you those are separate events. The inactivation and the closing of the gate are two separate events. And so they don't interfere with one another. So what you're imagining is there's a time when the gate is open and the ball and chain is letting ions through. It hasn't quite properly plugged the channel. And so you have this intermediate state. That doesn't seem to occur. That you don't get a state where you're partially inactivated. At least, better be a little careful of that. There are probably mutations where that happens, because there's some times these channels get leaky, and that has important clinical effects. But as far as I know, if things are working properly, this inactivation gate, the inactivation event, ball and chain, is separate and distinct from the channel event, or the gate event, where we have to close it. How are we doing for time? Oh, terribly. Okay. Are there any other questions? Because I got to move on. So what we have done here, let me go to the next slide. And this next slide will summarize a whole lot about what we've just talked about. And it's going to take some practice with this slide, because this is a fairly complicated slide. But let me walk you through it. This black line represents the change in voltage. So again, we go, now they're showing minus 60 here, and I'll tell you why in a moment. They go from minus 60, they start to open the channels, they reach threshold at maybe about minus 55, something in here. The action potential fires. We see the depolarization go to plus 40 and come back down again. But now this green line, what the green line is representing is it's representing an increase in sodium permeability. If you were talking about this in electrical terms, it'd be an increase in conductance, but it's the same thing. So the green line shows us the number of open sodium channels. So it shows you all these sodium channels opening very quickly. In parallel, we depolarize the membrane. And then at the peak here of the opening, at this point, those sodium channels now begin to inactivate. The ball and chain moves in. So now we have fewer and fewer of these open sodium channels. But now, look at this. This is the open potassium channels. This is the delayed rectifier. So it takes a while for these guys to come on. But they do come on, and then there's this crossover where now we begin to get more potassium permeability than sodium permeability, and we drive the membrane potential back down to the equilibrium potential for potassium. So opening the sodium channels drives the membrane potential toward the equilibrium potential for sodium. Opening potassium channels drives the membrane potential back toward the equilibrium potential for potassium. But you'll notice here that they've separated these, and that's truth. What I've done is I've said, oh, our membrane potential is going to be the equilibrium potential for potassium, but that's a lie. And the reason it's a lie is that at rest, those voltage-gated sodium channels are constantly flickering open and closed. They're just kind of a little unstable. So they're flickering, so there's constantly a little bit of background permeability to sodium. Back to the mantra. Membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Well, the permeability is clearly dominant to potassium. Way more potassium leak channels open than these flickering sodium channels. But we have a little bit of sodium permeability. So because of the little bit of sodium permeability that's there in the resting cell, the membrane potential isn't exactly at the equilibrium potential for potassium. It's a bit depolarized because that's the flickering sodium channels. But over here, notice that when we repolarize the membrane, that the membrane potential comes precious close to the equilibrium potential for potassium. If you can see why that's happening, you pretty much understand what's going on here. Because what's happening, the reason why we get this so-called hyperpolarization is two effects. First, many of these sodium channels remain in the inactivated state. So they're not available to flicker open and closed. So we have fewer available sodium channels to contribute to sodium permeability. And at the same time, if you look at this curve for the open potassium channels, we still have quite a few voltage-gated potassium channels open at this time, sort of in this time frame. So now we're looking for a short period of time when the sodium channels are mostly inactivated, so we have very few of them available to flicker open and closed, and we have a predominant open set of voltage-gated potassium channels which are driving the membrane potential close to the equilibrium potential for potassium. So if you can walk your way through and explain why this potential is minus 60 rather than equilibrium potential for potassium, how this membrane potential is achieved by opening the voltage-gated sodium channels, and how we begin repolarization in part by closing these channels and at about the same time beginning to open the delayed rectifiers, and why having the delayed rectifiers open and the sodium channels in the activated state leads us to this sort of approach of the equilibrium potential to the, approach of the membrane potential to the equilibrium potential for potassium. You understand what's going on in here. If you can explain all that, you understand the action potential. So anything else? So this is all a lovely story which tells us about how we can change the polarity on the membrane. It tells us how we can change the charge from, minus 70 millivolts to plus 40 and bring it back down again. But it doesn't tell us very much how we can begin to use the signal for long distance communication. And remember, we said one of the characteristics of a neuron is the conductal region, or the axon, has within it the voltage-gated channels. So how are we going to use these voltage-gated channels with these characteristics to propel or propagate a potential from place to place? So that's where we're going now. I'm going to go to the back board, and I'm going to do this in a couple of steps. In the first place here, I'm going to draw two parallel lines. I'm going to imagine this to be a cylinder. And all along the length of this membrane, which is the black line, I'm going to put in the obligatory potassium leak channels. So these blue guys are the potassium leak channels. I'll label them. So these are K-leak. Now, in this thought experiment, biology doesn't do this, but in this thought experiment, what I want to do is that I want to put in, I have to use red because that's the way I started. I want to put in up here a group of these gated channels, and we're going to label these as the voltage gated sodium channel. We will include their counterparts. I'll put them in here with some, and label them as the voltage, let me go down here. Label these as the voltage gated potassium channels. Now, in this thought experiment, I'm going to put measuring devices along the length of the membrane. I'm going to put one here, and put one here, and one here, one here, and one here, another one down here. And what these measuring devices are doing, what these electrodes are doing, is they're measuring, I'll show this with a little arrow with respect to ground, they're measuring voltage. And if we imagine here that we can add positive charge, right here on the inside of the membrane, we add the positive charge, sodium comes in. We've basically just generated the action potential that we showed here. So this is that action potential, all right? We can now show the action potential that we showed here, down here at this measuring device. So if we show it as time and voltage, we'll see that it goes up to plus 40, back down again. That's our action potential. That's what we record here. We record the full excursion because we're right in the neighborhood, right smack dab up against these voltage-gated sodium and potassium channels. But now the question is, what happens to all of that positive charge that's come into the cell? What's its fate? Well, all on the membrane we have leak channels. The only path for positive charge to leave the cell is through the leak channels. So all of this positive charge, which we show here, is the action potential. This positive charge coming in at this site is now going to leak out of the membrane. So what I'm showing here is the potassium carrying positive charge out of the cell. Well, what I really should have done to be more accurate about this is not show the repolarization and only show the depolarization up to plus 40, because that's the positive charge. So now we want to ask what happens to this positive charge along the length of the membrane, and the answer is it leaks out. So if we take a measurement here of what this potential looks like, it's going to look a little like this. It's going to go up, rather than plus 40, it may go up to plus 20. Take a measurement here, it may go from minus 70 to 0 millivolts. Take a measurement here, it may go from minus 70 to minus 20 millivolts. Take a measurement here, it may go from minus 70 to minus, say, 60 millivolts. And by the time we get out here, we may go from minus 70 to maybe minus 69 millivolts. This is simply saying that the positive charge, which is coming into the cell at this site where we've clustered the voltage-gated channels, is going to leave the cell through these leak channels. And that we can measure that loss of charge by taking these electrodes at intervals along the membrane, and we'll see that much of this positive charge leaks out, so the potential gets smaller. We can say that the potential decays with distance. This term, the potential decays with distance, I should say the amplitude. This term that the amplitude of the potential decays with distance is simply shown by the fact that these amplitudes of these depolarizations are getting smaller and smaller and smaller as we go away, and that's because the positive charge has left the membrane, left the cell through the leak channels. This happens surprisingly fast. This, if you would generate an action potential at this point, you would see a potential that was no more than a millimeter within, you would see a potential that was no more than a millivolt within a few millimeters. Well, think about that for a minute. We know this can't work that way because you can imagine you walk up to a hot stove and you put your hand on a hot stove. You know that that signal is coming from the tip of your finger, going into the spinal cord, causing a reflex to pull your hand back. You know it's pretty darn fast. You don't put your hand on the stove and think, my goodness, this is going to be hot. I better pull it away. It's a very fast reflex. So the next question we have to ask is how can we get this signal that we started out here to propagate from the tip of your finger back into your central nervous system, into your spinal cord, activate an interneuron, activate a motor neuron, and get your hand to pull away. How do we get speed out of that? And I'll leave you with that idea, because what we're going to do is we're going to walk through in 2 steps tomorrow. We're going to walk through first what happens if we take one of these membranes and we evenly distribute the voltage-gated sodium-potassium channels all along the membrane. Well, you can think about that for a minute. You'll see that we're going to sequentially open those channels. That's going to allow us to regenerate the action potential at each micro point, and it's going to allow us to propagate the action potential. So we'll do that first. And then we'll think about how we're going to propagate the action potential in myelinated axons. We touched on that yesterday. Think about the idea we're going to cluster those voltage-gated channels responsible for the action potential at the nodes of Ranvier. And then we'll sequentially open those channels and allow for the action potential to now hop from node to node. And we'll talk about how that gets done electrically when we come back tomorrow.